Hi. So today we are going to discuss about Python implementation part of digital signal processing. So some basics of Python implementation in um, Jupyter notebooks. So you import the libraries which are required. So mainly you will need NumPy for numerical manipulation and matplotlib for plotting, right? So this is some basic functions which we need. Let's say generate a sine wave with a frequency f0, sampling rate this much. So basically you first create the n is the sample index, right? Just from 0 to capital T into fs, right? Capital T is the total time duration of the signal, into fs will give the number of samples, right? So this is the number of samples. So it's a range 0 to number of samples minus 1. T is simply n upon fs, right? It's the continuous time corresponding for each sample. And x is my signal. Now x is simply sine 2 pi f naught t, right? Sine 2 pi f naught t plus some phase if you want, some phi, right? Now for discrete plotting, for continuous plotting, these are simple functions. Now generate a signal. So what we are doing here is simply x comma t, generate a signal of frequency 5 hertz, where sampling rate is this much, and total duration 1 second, right? So this is, so you will get 5 waves in your 1 second signal, right? Because the frequency is 5 hertz. And then I have plotted it, plot continuous x comma fs. So x is my signal and fs is the sampling rate. Now add some Gaussian noise to your signal. It will look like this. Basically you add, you know how to generate noise, np.random.normal for Gaussian noise with a mean 0 and standard deviation 0.1. And the length is length of x. So this is also very simple. You generate and then plot it. Now we come to an important part. Now we are going to move to filtering. How do we filter the signals? So let's see how do we implement some of the basic components required in filtering. So one very important component is the polynomials. So what are polynomials? Basically, if you remember, your transfer function is h of z, and it has a rational form. We are considering mostly rational form, means the numerator is a polynomial of z, denominator is a polynomial in z. So for polynomials in Python, we use np.poly1d function, or this is a function to represent polynomials. So let's see how this function works. I will say p is a polynomial, np dot poly1d 1, 2, 3. These are the coefficients in decreasing power of x. So if I run it, I get 1 x square 2x plus 3. 1x square plus 2x plus 3. So this is the coefficient of the largest power, which means from index, 0th index, first index, second index. So x square, x and x to the power 0, which means 1. Now, if I want to find the roots of this polynomial, basically this representation is very useful. I find it very useful for finding the roots. So I give the polynomial and I want to find the roots. So if I simply use p dot roots, it gives me 2 roots. So minus 1 plus 1.4j and minus 1 minus 1.4j, because this is all coefficients are real. So you know the poles, the roots will be conjugate, complex conjugate of each other, right? Now, another useful feature of this poly1d function is that you can, whatever output comes, you can multiply them just like you multiply any two polynomials. So let's say p and q are two polynomials, both are same. And if I multiply the two, it gives me the polynomial of degree 4, right? Very useful. And I can find the roots, again, very useful. Similarly, I can do multiplication, I can do division as well. You see, if I divide two polynomials, let's say this is a is a polynomial x minus 1 and b is a polynomial x minus 2, then if I say c is a into b, so a into b divided by b, it should give me a, right? And that's what I get. It's the numerator comma denominator. Numerator is a, the denominator is simply 1. Okay. Now this is the, let's come to the transfer function representation. Means transfer function is h of z, which means y of z upon x of z. So this is the notation which we'll be using to represent a transfer function. Basically, the b's are the coefficients of numerator, and the a's are the coefficients of the denominator, right? And they are in the increasing power now. So keep in mind there are some differences in notation. This is inbuilt in Python. I can't help this. Okay, so first is, given a transfer function, can I plot the pole zero diagram for this transfer function? Okay, so I have written this function. Okay, you draw the unit circle first of all, and then you have to draw the zeros. So given the zeros and poles, I have to draw the pole zero diagram. So simply I put a circle wherever zero is required, and I put a cross wherever the pole is required. That's it. If I run it, it will run. So okay, so now I want to test this function with a simple transfer function. So what I'm using here is a Butterworth filter. So 3, 0.05 are coefficients of Butterworth filter. It's a low pass filter, and this command, this function will return b comma a. B are the numerator coefficients, a are the denominator coefficients. And if I print b comma a, it gives me this, right? These are the coefficients of numerator, coefficients of denominator. So that's it. And now I want to use this. I want to plot pole zero diagram for this transfer function. How do I do? So first of all, I remember now the input of my pole zero plotting function are zeros and poles, and these are not zeros and poles, these are the coefficients, right? So from coefficients I have to extract the zeros and poles. What do I do? Simply convert them into a polynomial and find the roots of the polynomial. So I have simply converted this to a polynomial, and I have found the roots of the polynomial. So zeros are the roots, poles are the roots, and I simply pass this to my function, plot pole zeros, and that's it. So I got this plot. So I have gotten zeros. There are 3 zeros at about -1, about -1, about -1. So all 3 are at -1, 0, -1 plus 0j, right? And all the poles, there are 3 poles here, and this is the first pole, which is 0.9 plus 0.12j, 0.9 minus 0.12j, and 0.8. Okay. Is there some mistake here? Looks like. It should be a real, and this should be imaginary, right? Yes, real, and this should be imaginary. This should be real. X-axis is the real, and y-axis is the imaginary part. Yes, this is correct. Now this is, because my coefficients are real, I found how could the poles not be complex conjugate of each other. So this is the right representation. Basically, I did some mistake here. Again here, anyways, this one is fine. Okay, so the real axis and the imaginary axis. So this is how the Butterworth filter looks like. Now remember what we studied in our when we were doing filter design. We saw that there are poles around omega equal to 0. So omega equal to 0 will have a high value, and there are zeros around omega equal to pi. So they will pull it down at the at pi and minus pi, right? So obviously it's a low pass filter. You have read it in theory, and now here it is. Okay, now can I plot the corresponding h e to the power j omega, the magnitude plot and the phase plot? Okay, so I have to write a function for that. So given the poles and zeros again, zeros and poles, and a is some scaling factor, and n underscore m, this is basically n minus m. So e to the power j omega n minus m, right? If I want to introduce some phase. Okay, so this plot is also very simple. You find out omega is my, first I create my omega axis, and then my h is simply a times np dot exponential. Basically, this is this first part. Now I have to implement the zeros and poles. So what I'm doing is h is simply, you keep multiplying these things. So now this is not a polynomial. I have not written it as a polynomial, but I'm just using the omega, which is the complete axis, and doing the manipulation over it, which is equivalent. Instead of writing it as a polynomial, I'm writing it like this. Okay, I mean value by value, I'm computing. So then I find the magnitude of h, which is the absolute value of h, and the phase of h, which is the angle of h. And then just I'm plotting it. So how it looks like. So this is how it looks like. You see, around omega equal to 0, it has got high value, very high value. And around omega equal to pi, it is almost 0. Because those zeros are clipping it down, holding it down to 0. And the poles around 0 omega, they are pushing it up. So that's what you see. And similarly, the phase plot will be something like this, right? We have discussed it somewhat in our discussions. Okay, now let's come to filtering. Now, how do I actually implement a causal LCCDE, right? So I saw how to plot the pole zero diagram, how to plot the magnitude and phase diagram of h e to the power j omega. Now, how do I actually use an hz to filter my signal in real time? Means it's a causal filter. So SciPy gives us a SciPy is a library which gives us a function lfilter, scipy.signal.lfilter, to do this filtering. Although we can also write it ourselves. It's just a convolution, right? A simple convolution. But okay, let's use what is already available to us. Okay, so now I am here again, getting a Butterworth filter, same b comma a. Now I'm generating x sinusoidal signal, adding a noise as we have done above, a Gaussian noise with the standard deviation 0.1 and 0 mean. And I use L filter b comma a. So the format is the syntax is you pass on the b comma a comma the signal. So b comma a comma the signal. That's it. And I got y, and I just plot it, and this is how it looks like. So you can see there is a significant delay, right? My input versus output, there is a delay. That is why we were discussing zero phase transfer functions, so that the delay is totally zero. Delay is not there. So what was the idea? You, instead of doing just, let's say, instead you have hz square, means h e to the power j omega whole square, like as we have seen in the practice problem for zero phase transfer functions. H e to the power j omega mod whole square is given to you. This is what you want to implement. So this has got zero phase, but how do you implement it? So you know from theory that you have to write it as hz, h star z, right? You basically want to split it up into two parts. So if I draw the pole zero diagram, it's something like this. So you want to take only the poles which are inside, and the zeros are not required. Zeros can be anywhere, right? They don't affect your stability. The poles should be only inside. So my 0.2 pole should be inside. So means this is my h of z, and this will be a part of h of z inverse, or h star of z, right? And in this way, I could split. Now this 0 could be a part of either hz or h star z, doesn't matter, right? So these two possible implementations I will get. So this is my h of z, which has got a pole at 0.2. It's a stable causal filter, right? And this one, hz inverse, is simply the z inverse part of it. It is also h of z inverse is not stable, but h of z is stable. So we have to invert. Okay. So we discuss this in theory. So basically, this is the function. This is the filter which we want to implement, right? And we will be using time reversal filtering. So we will be passing through hz, then reversing the signal, passing it through hz inverse again. Means the hz again, and then again reverse my signal, right? So this is how I do it. So first of all, to find the roots, I just use this function to find the roots efficiently. Now I came to this hc is 2 times 0.3z plus 1 upon z minus 0.2, right? You can confirm this is the thing. Okay, and I represented it like as powers of z inverse. Now this is my corresponding polynomial form, which so basically my b's will come from here. B0 is 0.6, B1 is 2, right? So 0.6 and 2. My denominator A is 1 here, and A1 is 0.2, minus 0.2. And that's what I have written here. Now again, I generate the same signal. Now until here, everything is same. Now I have a u which is just filtered through this h of z, right? Until here, no problem. Now comes the time reversal part. So I reversed first my u. Now this will reverse my u, right? All the coefficients are read backwards. So it is reverse signal. And I filtered it with the same hz. And then again, the output was again reversed, right? So this is time reversal filtering. Let's see what is the final output. So this is my final output. This blue one is my x, the orange one is my u, means which will be the intermediate output, and y is my final output, which is the time reversed filtered signal. Okay, and so since here everything is very far, so what I have done here is I've plotted x noisy divided by max. So basically I divided everything by max so that everything comes to the same scale and I can compare. So what you see here is my un has a slight delay, right? The orange signal, it's slightly delayed, but my y has no delay, it comes back. It's not very much clearly visible here because the filter which was given in the example was anyways didn't have much delay in it, but this is the idea that the delay will be 0 with this time reversal implementation of zero phase filters. So I hope things make more sense now, and the main functions which we used here are mostly NumPy library, and in SciPy library we used lfilter just to implement the filtering part, which is basically just convolution. Okay, that's it. Thank you very much.